Hello, and welcome to CE Solutions. Today's lesson, we're going to talk about mathematics for EMS Advanced. My name is Caleb Frady. I'm a full-time EMS educator in North Carolina, work part-time as a paramedic in a rural county here in North Carolina. Also, I have a bachelor's degree in emergency medical science and hold a level 2 instructor certification in North Carolina. The objectives for today's lesson are as follows. First, we're going to analyze factors attributed to medication math errors to reinforce the importance of accurate medication calculations in pre-hospital medicine. Next, we will demonstrate relevant unit conversions to determine drug dosages, concentrations, and weight. Third, we will illustrate the formulas required for accurate medication dosing. And lastly, we will apply mathematics to EMS-related case studies requiring accurate medication calculations. Medication errors are a common occurrence, not just in pre-hospital medicine, but medicine in general. The Agency for Healthcare Research and Quality conducted a study in 2024 where they found that adverse drug events accounted for 39% of all of the adverse events that occurred in the inpatient setting. Of those 39%, 27% were preventable. So this study focused on multiple different locations throughout medicine, including ambulatory settings. They focused on medication-related alerts, ordering, and administration processes. So was the medication concentrated differently? Was the drug dose not standardized? Did the provider get the dose wrong and relay that? They focus on those types of events for this data. Cicero et al. In 2020 found that 42% of paramedics with 4 or more years of experience scored less than 50% on a drug math assessment. This highlights that drug math is a perishable skill. If we don't train on it and review it periodically, we're going to lose the ability to accurately provide the correct medication dosage to our patients in high stress environments. The study also concluded that medication errors are common in pediatric patients and strongly linked to complex medication calculations under stress. Walker et al. Concluded in their 2023 study that medication errors are an underreported problem, and this complicates our understanding and grasp of the issue. They also offered some insights into different ways to improve the reporting of medication errors. This could include establishing systems for this purpose. Those systems can be improved through a fair culture, anonymous reporting, or processes that ensure confidential and supportive management of incidents. So in other words, when a medication error does occur, it becomes a training point so that it doesn't happen again in the future. And leaders within EMS should look to determine the root cause of the medication error and take steps to correct it. Walker et al. Also highlighted some of the factors associated with medication errors as both physical and psychological. Now, their study included both quantitative and qualitative research methods to interpret the data and present their findings. And they found that some of the factors that contributed to medication errors included fatigue, poor lighting, excessive noise, distractions, uncontrolled or dangerous environments. All of those types of factors contributed to a clinician's ability to make sound clinical decisions and utilize safe medication practices. Now, many of those are uncontrollable, but some of them are, such as ensuring you have proper lighting. You're familiar with the medications that you administer and their concentrations and your dosage. Having resources to be able to utilize if you forget something. Another contributing factor to medication math errors is that it involves the input of several data points to determine the correct dose. For example, those points may include a patient's weight, desired dose, a drop set, a medication concentration, a time to administer it, etc. So the point from this is there's a lot of room for error during a very stressful call. There can be many different ways to reduce medication errors. Walker et al. Presented cross-checking medication details as a method that's been shown to be a significant protective factor preventing against medication errors. So this would include cross-checking the medication's dosage, the concentration of the medication, how much you intend to give, all of that, the right patient, right time, all of that before you administer the medication so that multiple different providers are seeing and hearing what medication is about to be administered and how. B and Connie, in a 2022 study, found that the implementation of a pediatric drug reference chart increased correct drug dosage rates by 30%. Now, their study was a simulation training study used to assess the efficacy of a reference chart. So they found that it increased the correct dose for Versed, dextrose, and epinephrine in pediatric patients. One caveat, however, is that the overall ability of paramedics in this study to administer the correct dose was still only about 68%, even with a pediatric drug reference chart. So this just highlights that while pediatric drug reference charts, like the one you see here on the screen, are extremely helpful in high stress scenarios involving critical patients, they should not replace our ability to do drug math and to memorize our drug dosages and our concentrations. We should use these reference charts simply as a tool to ensure that we're providing accurate medication dosaging to our patients. The drug reference chart you see on the screen here is an example of a pretty good reference chart. It includes the condition with the medication for that condition beside it. It includes the medication concentration, which is extremely important because if the concentration is different than what's on the chart, your drug dosage is wrong, which is why you can see in the red it says to confirm the concentration of the medication you actually have on hand. It gives you the dose of the medication and the volume that you would need to administer. But please keep in mind, we should not be over reliant on reference charts to find or give us the answer. We should be familiar with the medications that we administer as paramedics. As we move further into this lesson, one thing I've learned with medication math is you have to keep it simple. You have to pay attention to small things that are going to give you the answer without having to do a lot of math anyway. For example, the vial of fentanyl on your screen here. It tells us that it has 100 micrograms of fentanyl in 2 milliliters. And then right under that, it tells us that there's 50 micrograms per milliliter. So just by looking at this vial, we should be able to relatively easily determine our desired dose of fentanyl. Also want to highlight as we move through this lesson, I'm going to show the process for the medication math calculations, even though the answer may be obvious. The point of this is to reinforce how to get to the right answer so that when you're presented with a more difficult problem, you know how to get the correct answer. When is the last time that you trained on medication math? We know this is a perishable skill. We don't train it as often as we do airway or cardiac conditions. Calculating drip rates and medication infusions are not necessarily a day-to-day occurrence in pre-hospital medicine. And in the pre-hospital environment, when medication math is needed, it's often a high acuity and high stress call, which complicates our ability to correctly calculate the dose. So how can we reliably administer correct and accurate medication dosaging if we don't train on something continuously like we train intubating patients or starting IVs on a day-to-day basis? Some helpful tips that I give to my students to help them with medication math are I encourage providers to do the math manually every single time when they're practicing and use the cheat sheet as a tool to confirm your answer. Repetition is the only way to master med math. You have to learn the patterns, you have to memorize the formulas so that you can achieve the right answer when the protocols are taken out of the truck or the drug reference chart fell off and flew out the window. On the topic of calculators, I'm a proponent of using calculators. It's a tool that we have just like anything else. However, like any tool, we should not be fully reliant on a calculator. My recommendation is that while you're learning the formulas, you're learning the patterns of medication math, use the calculator to help you get past the long division or the long multiplication or dividing by fractions that may bog you down in the medication math so you can see the actual process of achieving the correct answer. And then once you have a firm grasp on the process of inputting the data points and achieving the correct answer, then remove the calculator and do it without a calculator and check your answer. The first step in being able to calculate accurate medication dosages is to understand how medications are measured. Well, most commonly they're measured in mass units. The most common ones are grams, milligrams, and micrograms. Now, milligrams and micrograms are smaller units of measurement compared to a gram. What would be a larger unit of measurement to a gram would be a kilogram. Typically don't see medications packaged in kilograms, as that's what we typically use for weight and not medication weight, for example. Now, when we look at grams, milligrams, and micrograms, a gram is kind of where everything starts, and then from there, the smaller units of measurement are divided into one thousandths. We can say that a milligram is one thousandths of a gram. Right? So one thousandth of a gram. For micrograms, we can then say that a microgram is one thousandth of a milligram. Each step down that it goes, it's a multiple of 1,000 or three decimal places that we'll get to in just a minute. Now, what if we needed to go from grams all the way to micrograms? Well, that becomes pretty easy if we know that milligrams are in the middle. That's six zeros, so six zeros is 1 million. So then we would look at this and say, okay, so a microgram is the same as saying it's one millionth of a gram, right? And then the gram is where we base everything off of as just a one. By knowing how these mass units are weighted compared to the gram, we can simply move the decimal place to the right or to the left to convert very quickly between the different units of measurement. Now, this also works with milliliters and liters, where a milliliter is one thousandth of a liter. Milliliters and liters are volume units of measurement, whereas grams, milligrams, and micrograms are mass units of measurement. So now let's look at a couple examples. Say for starters, we wanted to go from grams to milligrams. And I have on hand 0.75 grams, and I need to know how many milligrams that is. Now, the reason we would most commonly need to convert between grams, milligrams, and micrograms in a medication math problem is because we need our units of measurement to match. For example, if our dose of the medication is in milligrams, but it's packaged in grams, we need to convert the grams to milligrams so that they both match. Otherwise, our math isn't going to work the way that it should, and we'll get an erroneous answer. So to convert from grams to milligrams, we know that a milligram is one thousandth of a gram. So because it's one thousandth, there's three zeros, we're going to move the decimal three places. Now, because a milligram is a smaller unit of measurement, we're going to move the decimal three places to the right. So we can come in here, put it in black for you. One decimal place, two, and three would be right there. So our answer in milligrams is going to be 750 milligrams. We achieved that simply by moving the decimal place. If we needed to convert it back into grams, we would just move the decimal place three places to the left. Let's move on to a different example. Say in this example, we have 2,500 milligrams, and we need to convert that into grams. Well, because we know that grams is a larger unit of measurement, right? Instead of moving the decimal place three places to the right and having a larger number in front of our grams, we need to move the decimal place three places to the left. So we're going to take our decimal here, which is located here, 1, 2, 3, and our answer is going to be 2.5 grams. On the screen, I put three more practice examples, so take a minute, pause, work these problems quickly, and then come back and we'll go over the answer. The first problem we have is we need to go from milligrams to micrograms. So we have 0.2 milligrams. So by moving the decimal point three places from where it's at, we're going to end up with 200 micrograms. The second problem here we have is we have 4,000 micrograms. We need to convert that to milligrams. Because milligrams is a larger unit of measurement than a microgram, the decimal place is going to get moved 3 places to the left. So our answer in this case would become 4 milligrams. And the last one is an example we haven't seen yet. Remember I said that milliliters and liters work the same way as grams and milligrams. So we know that a milliliter is a smaller unit of measurement compared to a liter. So we're gonna need to move our decimal place 3 places to the right. And that's gonna give us 5,000 milliliters. These unit of measurement conversions are essential to be able to get the correct answer with a medication math problem. And it's something that we do quite frequently when answering these problems to get our units of measurement to match on each side. Now that we've learned about the units of measurement, it's also important to understand how medications are concentrated, right? So typically what we see is our parenteral medications are represented as a concentration. And that concentration is essentially a ratio between mass units of measurement and the total volume that the medication is dissolved within. So we can show this pretty easily, and most of us probably do it every day. In this cup here, I have 27 grams of an electrolyte powder. And I'm going to take this 27 grams of powder and I'm going to put this into a 250 milliliter water bottle. So when I dump that in there, the 27 grams of electrolyte powder, it doesn't disappear, it simply dissolves into the water, right? So give it a couple shakes and all those particles are inside the water. So now inside of this container, I have 27 grams in 250 milliliters of water. So in the water bottle example, that would be expressed as our concentration by writing 27 grams in 250 milliliters of water. And that would be the concentration of that electrolyte drink. We can see that through numerous different examples of medications. For example, epinephrine 1-to-1 is packaged 1 milligram in 1 milliliter. Other medications may be packaged 10 milligrams in 2 milliliters. So for every 2 milliliters that you draw up and give to a patient, you're giving that patient 10 milligrams of the medication. Other examples that would apply to medication infusions, say you have 1 milligram of a medication that is mixed in with 1,000 milliliters or 1 liter there. You may have another medication that is packaged in 4 milligrams, and that's dissolved into 250 milliliters. All of these are medication concentrations. It's extremely important for us to understand the concept of medication concentrations because that's going to come into play later when we start to apply formulas to be able to determine the correct medication dosage. The concentration is key in determining those answers. Being able to reduce a medication concentration down to the amount of drug that's in a single milliliter is a critical step in medication math. You can use a calculator for this and simply divide the mass by the volume or the top number divided by the bottom number, and that's going to give you the answer on your calculator. And there's also a shortcut, a way that bypasses the use of a calculator and is really good to use in stressful scenarios in the field where it may be difficult to get a calculator out and actually input that data. You can do this on your glove, on a piece of paper, or in some cases, just even in your head and be able to get the right answer relatively easily. So this shortcut will only work when your denominator or the volume that the medication is concentrated in is a factor of 10, 100, or 1000. So I'm going to show you a couple of examples and show you how this works. So let's start with an easy example to show that this process works. And let's say that we have a medication that's packaged 10 milligrams in 2 milliliters. And we need to know how many milligrams are in a single milliliter. So we can look at this and pretty easily say that, hey, 10 divided by 2 is going to give us 5 milligrams in 1 milliliter. And the 1 in front of the ml, we don't have to write that. We just know that it's there. So with this factor process, what we're trying to do is we're trying to take the bottom number, the denominator in this case, and multiply it by a number that's going to allow it to become 10, 100, or 1,000. And when we do that, that's going to allow us to move the decimal place and change the other side to determine our concentration. So let's say 2 times 5 is going to equal 10. So our factor in this case is going to be 5. So 2 times 5 is going to be 10 milliliters. And remember, what we do to one side, we have to do to the other side. So 10 times 5 is going to be 50 milligrams, right? Now, because there's a 10 at the bottom number, we're able to move the decimal place. So when I do this to the one side here in green, that's going to get me to 1 milliliter on the bottom, which is where I want to be. And then I must do that to the other side and move the decimal place one place. And that's going to get me to 5, which is where I want to be. So you can see that with this process, we get the same answer. So now that we kind of understand how the process works, let's move to a slightly more difficult medication concentration to determine. And say that we have a medication that we have packaged 1 milligram in 100 milliliters. Now, this factor method is most often used for medication infusions, and we're going to talk about those in depth later in the lesson, and we'll come back to this shortcut in those examples. So our medication is 1 milligram in 100 milliliters, and we need to know how many milligrams are in 1 milliliter. So I'm going to write mLs down here at the bottom, and we're trying to figure out how many milligrams are going to be in 1 milliliter. Well, when we look at this, we know that our denominator is already 100. So it's already a factor. So there's nothing that we're going to multiply it by to get to a denominator of 10, 100, or 1,000. It's already there. So in this case, we can very easily just move our decimal place. So we move our decimal place 2 places to the left on one side and 2 places to the left on the other side. And that's going to give us 0.01 milligrams per milliliter. And that is going to be our answer, 0.01 milligrams per ml. So here's another example of a common medication concentration that we may need to determine the amount of drug per milliliter. But in this example, our medication dosage is in micrograms. So we actually want to know for this one, how many micrograms of this medication are in 1 milliliter. So with the factor method, it works the same way. 250 is going to go into 1,000 4 times. So our factor in this case is 4. So we're going to take that. Factor is 4. We do that to both sides. And we're going to find that we have 16 micrograms in 1,000 milliliters. So now that we're to a point to move the decimal place, we can move the decimal place 3 places to the left and get our 1. And then we can move the decimal places 1, 3 places here. But remember, this is still in milligrams. So when we move this decimal place, I'm going to write it over here. We're going to end up with 0.016 milligrams per milliliter. So to get to our microgram answer that we need, we just need to move the decimal place 3 places back to the right, and you can see that we're going to get 16 micrograms per milliliter. So this is what really makes this shortcut speed up and be very useful for medication infusions. So because we know that we're multiplying our IV bags of fluid by a factor, it's going to equal 1,000. For example, our IV bags of fluid come in 100, which we simply move the decimal place, 250 cc's, 500 cc's, and a liter bag. So our factors are going to be for 250 and 500. So factor of 4 or factor of 2, right? So we know that how many places we're going to need to move the decimal place. So we can just automatically do that. So when we do 4 times 4 and get 16, all we need to do is simply reduce it 1 mass unit and write 16 micrograms per milliliter, as you see on the screen here. So essentially what we're doing is we are skipping this step right here and just go ahead and converting the milligrams to micrograms, because we know that we would have done that in the middle of this process. Let's show that to you one more time. Say we have a medication that's concentrated 1 milligram in 500 milliliters, okay? And we also need to know how many micrograms per milliliter this medication has. So our factor in this case is going to be a factor of 2. So 500 times 2, 1 times 2. Again, because we know we're going to have to move the decimal place 3 places to the left because 1,000 is going to be the bottom number, we're just going to go ahead and convert our 2 times 1 to micrograms. So 2 times 1 is 2. Change that to micrograms. We have a medication concentration of 2 micrograms per milliliter. And if we were to plug this into our calculator, we're going to get the exact same answer and just move the decimal place and we would get to 2 micrograms per milliliter.
Converting a patient's weight is a common occurrence with medication math. Most commonly, we're converting a patient's weight from pounds to kilograms, as most of our medications that are weight-based utilize kilograms for the dosing. We can use a calculator to get this answer. There's also a shortcut that works really well in the field when you need a quick answer, and you can most of the time do it in your head relatively easily. And that's to divide your patient's weight in pounds by 2 and then subtract 10%. So we know that 1 kilogram is equal to 2.2 pounds. So by subtracting the 10%, that's where the 0.2 comes into play here. So let's do an example so that you can see this in action. Say we have a patient that weighs 100 pounds. And this patient weighs 100 pounds, and we need to know how many kilograms they are so we can calculate the correct drug dose. Well, the first thing we need to do is divide 100 divided by 2. 100 divided by 2 is going to give us 50. Next, we need to subtract 10%. Well, to subtract 10%, it's 10% from 50, and the decimal place is right here. To do that, we just simply need to move the decimal place 1 place to the left, and that's going to tell us what 10% of 50 is, and that's going to be 5. So that becomes 50 minus 5, and that's going to give us our answer of 45 kilograms. So a 100-pound patient is going to weigh approximately 45 kilograms, and that's what we'd use for our medication math. This process will also work if you need to convert from kilograms back to pounds. It's just instead of dividing by 2, you would multiply by 2, and instead of subtracting 10%, you would add 10%. That's just not as common in medication math to need to do that.
Let's practice some weight conversion problems. Pause the screen, work these 4 problems out, and then come back and we'll go over it. The first problem, we have a 230-pound patient that we need to convert into kilograms. So using our shortcut method, we're going to take 230 and we are going to divide that by 2. When we do that, we're going to get 115. Now, the second part of our shortcut is we need to subtract 10%, right? So we're going to take this and we're going to move our decimal place 1 place to the left, which is moving it a tenth or 10%, and we're left with 11.5. So now we're going to take 115, we're going to subtract 11.5 from that, and that should give us 103.5 kilograms. Now in the field, we don't need to worry about the 0.5 kilograms. We can use 104 kilograms or 103 kilograms. I would most likely just round that up to 12 and do 115 minus 11.5 and get an answer of 104 kilograms.
Next, we have a 55-pound patient that we need to determine how much they weigh in kilograms. My first step would be to divide 55 divided by 2. That's going to give me 27.5. Now I'm going to subtract 10%. So I'm going to move my decimal place 1 place to the left. And this is going to become 27.5 minus 2.75. That will give me 24.75
kilograms, and I would round that up and use 25 kilograms as my patient's weight. The third one is a 34-pound patient. I'm going to divide that by 2, and that's going to give me 17. When I subtract 10%, that will become 17 minus 1.7, putting my answer at 15.3 kilograms, and I would use 15 kilograms. And our last one is a bit different. This one is a kilograms to pounds question. So instead of dividing, I'm going to multiply 130 kilograms times 2, and that's going to give me 260. Now I still need to determine what 10% of 260 is. So by moving the decimal place one place to the left, I have 26. This will become 260 plus 26, which will put my patient at 286 pounds.
Now we are ready to take a look at the formulas that are required to answer some of our medication math problems. The first formula that we have is the single dose formula. Now this formula is going to be used to calculate the amount of drug that we're going to give to a patient based on our desired dose. So the single dose formula would be an example of pulling a medication up out of a vial to give that medicine via IV, IO, or IM. The formula for this is your desired dose, which I'm going to write here as DD for desired dose. The desired dose should be in mass units, such as milligrams. For example, could be micrograms, could be grams, depending on how your medication is concentrated. Your desired dose is going to get divided by the amount of drug you have on hand. So for this case, I'm just going to write H for on hand. And this is also going to be in mass units like milligrams. And those mass units on the top and bottom, they need to match. So if our desired dose is in micrograms, but our vial of medication says milligrams, then we need to make sure we convert the milligrams to micrograms before we try to do our math by plugging the data points into the formula. Now, desired dose divided by what you have on hand is then going to be multiplied by the volume, right? So by the volume that you have on hand. So this is going to be in a milliliters. Once you do the calculations for this formula, your answer is going to be the amount of milliliters that you need to administer to the patient, and that's going to be correlated with your desired dose. In my practice with the single dose formula, it's not as commonly used because most often the first step when determining this is to reduce the medication concentration down to the amount of medication that's in a single milliliter. And then from there, you can typically figure out your desired dose in your head relatively easy. However, this formula can be something, especially in a stressful environment where maybe you're not able to do that math as quickly in your head when you're worried about other things. And writing this formula down, you can be confident that you have the right answer.
Let's look at some examples of the single dose formula. Please, for each of these examples, pause the screen and work the problem and come back for the answer. With this problem here, I need to give a patient 0.5 milligrams of a drug. I have a vial of medication that's concentrated with 1 milligram in 10 milliliters of fluid. And I know that this is the single dose formula where I'm going to take my desired dose divided by what I have on hand and multiply that by the volume. The first step to solving this problem is to reduce my medication concentration. So since I already have a factor of 10 in the denominator, I can simply go ahead and just move the decimal one place to the left on both sides. And that's going to give me a drug concentration here of 0.1 milligram per milliliter. Now that I've gotten this step done, most of us can probably look at this and say that we're going to need to administer 5 milliliters of this medication. And that's why I do that step first, because most often it negates the need to even need to use the single dose formula. But I'm going to show it here because some examples may not be as self-explanatory. So when I plug this into my formula, my desired dose is going to be 0.5 milligrams because that's what I want to administer to my patient. So it's 0.5 milligrams. And I'm going to divide that by the amount of medication I have on hand, which is going to be 0.1 milligrams. And that's going to get multiplied by the volume of 1 because I reduced it down to its concentration here. I'm only going to have to multiply by 1. So now I just simply need to plug in 0.5 divided by 0.1 milliliters here, and I'm going to get an answer of 5 milliliters. In this example, I need to administer 30 milligrams of a drug to a patient, and I have a vial of medication that contains 40 milligrams in 5 milliliters. So right off the bat, I know that 5 milliliters is going to be too much medication. So we know we're going to be somewhere around probably 3 to 4 milliliters to achieve this 30 milligram dose, but we want to be as accurate as possible. So we're going to do our medication math. The first step is to reduce our medication concentration utilizing our factor method. So since 5 is going to go into 10, we can multiply 5 by 2 on this side and do the same to 40 on the other side. And we're going to get 80 milligrams in 10 milliliters. So now that I have 10 as my bottom number, I can move my decimal place. Move it one place to the left, move it one place to the left, and we get a drug concentration here of 8 milligrams per milliliter. So now I have that done, I can start to input data into my single dose formula. And I'm going to take 30 milligrams, which is then going to be divided by 8 milligrams. And that's going to get multiplied by 1 to give me my answer. So if I was to do 30 divided by 8, I'm going to get 3.75. 3.75, and that's going to be multiplied by 1, which would give me an answer of 3.75 milliliters right there. We can see in this example that my desired dose is a bit different. It's weight-based, and I have a 55-pound 6-year-old. So to solve this problem, my first step is I need to figure out what my desired dose is. So the first thing I need to do is I need to convert pounds to kilograms. Well, to do that, we know that we need to divide 55 divided by 2, and that's going to give me 27.5. The second step is to subtract 10% from 27.5. I can determine what 10% is by moving the decimal place one place to the left. So 10% of 27.5 is 2.75. So if I was to minus 27 minus 2.75, I'm going to get 24.75. 24.75, we're going to round that up to 25 and say our patient is 25 kilograms. Okay, so now that I have that figured out, the next step is I need to multiply 25 times 0.5 to determine my desired dose. So 25 times 0.5 is going to give me a total desired dose of 12.5 milligrams. Cool. Next, I'm going to take a look at my medication and how it's concentrated, and I can see that it's already concentrated for me in the amount of medication I have in a single milliliter. So this step is complete. So my third and final step is to plug everything into my single dose formula and determine my answer. So I'm going to take 12.5. That's going to go at the top. So 12.5 milligrams. That's going to get divided by 30 milligrams, which is the amount of medication that I have on hand. and then that's going to be multiplied by 1 because it's already converted down for me. So now when I look at this to do this, I can see that milligrams will cancel out, so that all I'm left with is milliliters. 12.5 divided by 30 is going to give you a fraction that's going to be 0.4 milliliters that I will need to draw up and administer to this child.
There is two categories of drip chambers that we utilize in pre-hospital medicine. We have a macro drip chamber, which is best used when we need to administer larger volumes of fluid, like a fluid challenge over 10 to 15 minutes. A macro drip chamber would be best for that. Our macro drip chambers come in different drops per milliliter, and they can be in 10, see them in 15, and 20 drops. So GTT is the abbreviation for drops per milliliter. So every 10 drops is 1 milliliter is what that comes out to. Now our micro drip chambers are best utilized when we need to give a specific medication infusion to a patient. So 1 to 2 milligrams per minute would be an example of an infusion. And we want to be able to more accurately count the drops per minute because we want to be very precise with this infusion. Now our micro drip chambers come in 60 drops per milliliter chambers. And this is important because for the formulas moving forward, fluid over time and infusions, we have to take into account the type of drop set that we are using because that's going to affect our answer because it gets plugged into the formula. Our next formula is fluid over time. We're going to use this formula when we need to calculate the drops per minute to give to a patient that's based off a set amount of time. So our desired dose is based off a set amount of time. A common example is say that we need to give a patient TXA, and the dosing for TXA calls for us to put 1 to 2 grams of the medication into a 100 milliliter bag of D5W and give that entire 100 milliliter bag of fluid over 10 minutes. So because the dosing is over a set amount of time, that's how we know that fluid over time formula is what we need to utilize. So this formula is going to begin with the total amount of volume that you need to administer. So it's going to begin by volume, also referred to here in this formula as our desired dose. So our desired dose in volume is going to get multiplied by our drop set. So this is where taking into account the type of drop set you have is important. In fluid over time, a macro drip chamber is going to work best because the answer is going to be a manageable drops per minute that we can titrate pretty easily with those chambers. A micro drip chamber, in many of these examples in the field, you would get a very large answer and you essentially would just have to run it wide open and not really be able to calculate the drops per minute. Now, so you take your desired dose and your total volume, multiply that by your drop set, and then that is going to get divided by the amount of time that you need to give the medication. Now, then this is important. It should be the amount of time in minutes. So by having it in the amount of time in minutes, our answer is going to come out to be drops per minute, right?
In this example, I need to give a patient 250 milliliters in 1 hour. So that tells me, because it's a set amount of time, this is going to be a fluid over time formula that I need to utilize here. I have my drop set and I have my formula. So I have all the variables that I need to solve this problem. So I'm going to start with my desired dose, which in this case is 250, because that is the total amount of volume that I want to administer to my patient. That's going to get multiplied by the drop set that I'm using. For this scenario, I'm using a 10 drop set. So that's going to be 250 milliliters multiplied by 10 drops per milliliter. This is going to be divided by the time that I need to give this fluid. In this case, it's an hour. I'm going to convert that to minutes and place 60 minutes down here at the bottom. So now I'm ready to do my math across. I can go ahead and cancel things out. And what cancels out here is my milliliters. So my answer is left in drops per minute. When you plug this into your calculator, you're going to do 250 times 10, which is going to give you 2,500. And then you're going to do 2,500 divided by 60, and that's going to give you 41.6 repeating. So we're going to round that up to 42. And our answer here is 42 drops per minute. Now, how do we practically give this patient 42 drops per minute? Well, the best way to do that is to break that number down to a more manageable drip rate so that we don't have to sit there and count 42 drops for a full 60 seconds. So a couple things we can do here. And we can divide 42 divided by 20, and that's going to give us 2 drops every 3 seconds. 2 drops every 3 seconds. We can divide 42 by 10, and that's going to give us 4 drops every 6 seconds. We can divide 42 by 4, and that's going to give us 10 drops every 15 seconds. Or we can divide 42 by 2, and that's going to give us 21 drops every 30 seconds. So by dividing it by 20, 10, 4, or 2, we're basically just breaking down our drops per minute into specific seconds. They're going to be really easy for us to count in the field, so that when 60 minutes passes, this entire 250 milliliter bag of fluid is empty. Let's do one more fluid over time problem. For this patient, I need to administer 1 liter or 1,000 milliliters of fluid, and that needs to be given over 5 hours. Now, there's really 2 ways that you can do this. You can go ahead and convert hours to minutes and do your math that way and get your answer, or you can leave 5 as your time and just know that your answer is going to come out in drops per hour, and then you would need to divide your answer by 60 to get your drops per minute. Since we've done it the other way with minutes, I'll show you what it looks like leaving hours as our time and then dividing by 60 here. So I'm going to take 1,000 milliliters and multiply that by my drop set, which in this case is a 20 drop set. It'll be 20 drops per milliliter. That's going to get divided by my time. And so if we were to keep this as hours, it would be 5 hours here. So when I get my answer, I'm going to get 1,000 times 20 is going to give me 20,000. It's going to give me 20,000, and that is going to be divided by 5. So when I put that in, I'm going to get 20,000 divided by 5 is going to equal 4,000. Now remember, this is going to be in drops per hour. Drops per hour, because I didn't convert hours to minutes when I did my formula the first time. And I know that because the milliliters cancel out, so I'm left with drops per hour. So all that's left for me to do at this point is I need to take 4,000 drops per hour, divide that by 60, and that's going to give me an answer of 67 drops per minute.
Our third formula here is our infusion formula. And this is utilized when we need to calculate the drip rate for a patient based on medication to be given per minute. So if we have a drug that we need to give 1 milligram a minute, every minute that we're giving that medication, the patient should receive 1 milligram of that medication. So we need to calculate a specific infusion in drops per minute to titrate and give to our patients. This infusion formula is going to begin with our desired dose. And our desired dose should be the amount of drug that we need to give per minute. Now, I put milligrams here just as an example. It could be a different unit of measurement like grams or micrograms. Our desired dose is then going to be multiplied by our drop set. Now, in infusion calculations, best practice is to utilize a micro drip, 60 drop per milliliter drip set, so we can accurately titrate the drops per minute to what the patient needs. That is then going to be divided by our medication concentration, and I'm going to abbreviate that. Our medication concentration needs to be in the amount of medication per 1 milliliter, right? If we try to leave anything other than a 1 as the denominator, then we're not going to be able to use this formula and we're going to get an erroneous answer. Another thing with our concentration is we need to make sure that the units of measurement match. So if our desired dose is in micrograms, then our concentration, we need to convert that to micrograms per milliliter. Now, the reason that we do that is so that we can cancel things out and achieve an answer that is drops per minute. So when we come in to do our formula here and do our math, we can cancel milliliters out and we can cancel our mass units of measurement out, so the milligrams here, so that all we're left with is drops per minute. And then our answer would be our drops per minute answer.
Here, we need to give a patient 3 milligrams of a medication every minute. We have the medication concentration of 1 gram of the drug mixed in with 250 milliliters of fluid, and we have a 60 drop per milliliter set. So this is going to be an infusion formula. The first step is I need to reduce my drug concentration so I can input the data into my formula. So we're going to use our factor method, which is 250 times 4 to make 1,000, 1 times 4 here, and since our desired dose is in milligrams, we can skip the step in the middle of our factor method like we learned earlier and simply change it to milligrams. So it's going to become 4 milligrams per milliliter. Now that I have my concentration, I'm ready to put all this information into my formula. So I'm going to have 3 milligrams per minute as my desired dose. That will be multiplied by my drop set, which is a 60 drop set here. And then I need to divide that by my drug concentration, which is 4 milligrams per milliliter. So looking at this, I can start to cancel things out. Milliliters will cancel out and the milligrams will cancel out. So my answer is going to be in drops per minute. The first step is to multiply across the top. That's going to give me 180. And then I would divide that by 4, which is going to give me an answer of 45 drops per minute. I would then divide that by 10 to give me an answer of 4.5 drops every 6 seconds. So I can titrate that, round that up to 5 drops every 6 seconds, and I'm giving this medication infusion. In this example, we need to give a patient a medication dose of 5 micrograms per minute. We have our medication concentrated with 1 milligram of our medication in 500 milliliters of fluid, and we're using a 60 drop set. So because we can see in our desired dose that this is a specific amount of medication per minute, this is going to be an infusion problem. First step, as usual, is going to be to reduce my medication concentration with our factor method. So 500 times 2, 1 times 2, drop it 1 mass unit. We're going to have 2 micrograms per milliliter. So there's my concentration. Now I'm ready to input this information into my formula. So I'm going to have 5 micrograms per minute. And that will be multiplied by my drip set, which is a 60 drop set. I need to then divide that by my medication concentration, which is 2 micrograms per milliliter. I can go ahead and start canceling things out. Milliliters cancel out, milliliters cancel out, micrograms cancel out, and micrograms cancel out. Now, say for example, we forgot to do this step right here where we reduce our concentration down and change it to micrograms, and we tried to leave milligrams right here, we wouldn't be able to get the right answer because our mass units of our medications are different and they're not matching. So keep that in mind. You cannot forget that step or you won't be able to get the right answer. So then I would just multiply across the top. So 5 times 60 is going to give me 300. And that gets divided by 2, which is going to equal out to 150. So I have an answer of 150 drops per minute. That's a multiple of 10, so divide 150 by 10, and I'm going to get an answer of 15 drops every 6 seconds. There's 60 seconds in a minute. So there's my answer. The drug dose in this problem is a bit different. It's in medication to be given per hour instead of minutes. So I'm going to show you how I'd work this problem. This is an example of a diltiazem drip where we have an infusion range is typically 5 to 15 milligrams an hour. I just went with 5 for this example. And we make that medication by putting 25 milligrams of our medication into a bag of IV fluid. For this example, I just went with a 100 milliliter bag of fluid, and I have a 60 drop set that we're going to be using. So first step here is I still need to convert my medication down, but since I already have it in milligrams on both sides, I'm not going to convert it to micrograms. And since I have 100 here, all I need to do to reduce this is simply move the decimal place 2 places to the left on both sides. 2. So I'm going to have a drug concentration of 0.25 milligrams per milliliter. Perfect. So I can go ahead and plug this into my formula this way, but just keep in mind my answer is going to come out in drops per hour, and then I would divide that by 60 at the end. So let's write all this down. So I have a desired dose of 5 milligrams per hour, which is going to be multiplied by my drop set, which is a 60 drop set. 60 drop set. And then I'm going to divide this by my drug concentration of 0.25 milligrams per milliliter and work our problem here. So canceling things out, milliliters cancel out and milligrams cancel out. So I'm left with drops per hour. 5 times 60 is 300. 300, and that's going to be divided by 0.25. Now, this is one of those examples where I would need a calculator or I would need to write it down longhand. So this is what I was kind of talking about earlier with, keep it simple, use a calculator as a tool, get proficient with the formulas, with the process, and then remove the calculator and start to learn how to do the long division here. So 300 divided by 0.25 is 1,200. So I'm going to have 1,200 drops per hour. And then I'm going to take that and I'm going to divide that by 60, which is going to give me an answer of 20 drops per 20 drops a minute is pretty manageable for us to titrate. I can take 20 and I would probably divide that by 4. Divide that by 4, and I would give this patient 5 drops every 15 seconds. That's pretty manageable to slow that rate down and count that with a 60 drop per milliliter set. It's also important for us to have a general understanding of how long our bag of medication is going to last at our constant drip rate. If we do titrate it, then that would change how long it lasts. But say that we kept it constant at 20 drops per minute, how long will this 100 milliliter bag of medication actually last? Well, 20 drops per minute with a 60 drop set, it's going to take me 3 minutes to give 1 milliliter of this medication. So I can just times my, so I would just multiply 3 times the amount of volume I'm using, which is 100, and that's going to give me 300. So it's going to take 300 minutes or 5 hours for this entire bag of medication to be given. So if we do have a long transport and this patient's going to be on this medication for a very extended period of time, then I may need to make a new bag of fluid. But in general, 911 pre-hospital medicine is not necessarily a concern.
The formula for a weight-based infusion is going to stay the same. We're still going to take our desired dose in the amount of mass unit of measurement to be given per minute, multiply that by our drop set, and then divide that by our medication concentration. All right, and remember again, our medication concentration should match the unit of measurement as our desired dose. So it would be micrograms per milliliter. And our answer in that case will still come out and it will still be our drops per minute answer. Right, so our drops per minute here. Now, the only extra step that we're going to need to do with a weight-based infusion is we need to multiply the desired dose by the patient's weight in kilograms. We would take our desired dose, in this case it'll be desired dose in micrograms, for example, and we would multiply by the patient's weight in kilograms. Right? By doing that, the answer in this case is going to be the amount of medication that we need to give the patient every minute. So the only extra step with a weight-based infusion is we just need to manually figure out what our medication to be given per minute is, because it's a weight-based medication, so we have to multiply by that by the weight first. Once we've done that step, we're ready to plug everything into our formula and calculate that and get our drops per minute answer.
This example, I have a weight-based medication infusion that we need to administer. Also pay attention that the units of measurement of the drugs currently do not match, so I need to make sure that I change that. The first step here is I need to determine what my actual desired dose is per minute, and to do that, I already know my patient's weight in kilograms, so no conversions needed there. I'm going to take 10 and multiply that by 90, and that's going to give me a desired dose of 900 micrograms per minute, would be this first step. Next, I need to go ahead and convert my drug concentration down. So 800 milligrams in 500 mLs is a pretty standard concentration for dopamine, which is one of our weight-based infusions. And I'm using my factor method, so I'm going to say, okay, well, 500, the factor here to get it to 1,000 is going to be 2. And I'm going to do the same to the 800. And that's going to give me 800 times 2, we know is going to be 1,600. I can reduce that one mass unit because I need to get it to micrograms here. And that's going to give me 1,600 micrograms per milliliter. From this point, I have everything I need to plug this in to my infusion formula like we've been doing. So I'm going to take 900 micrograms per minute, multiply that by my drop set, and then divide that by my concentration, which is 1,600 micrograms per milliliter, and work the problem. Well, this is going to be a pretty large, 900 times 60 is a pretty large number. It's going to give me 54,000. So I got 54,000 divided by 1,600 micrograms, canceling things out. Milliliters cancel out, and my micrograms will cancel out. If you forget to do that first, then you'd be left with kilograms inside your formula, and you wouldn't be able to get the right answer. So now I need to do 54,000 divided by 1,600. That's going to be a calculator problem for me. And I'm going to get an answer of 33.75 drops per minute. Cool. So now I have my drops per minute. I can convert that down. 33, we can round that up to 34. Divide this by 10. And I'm going to get 3.4 drops every 6 seconds. It's pretty manageable. I'd probably just go ahead and round that up to 4 drops every 6 seconds is what I would actually give to the patient here. And this is an example of a weight-based medication infusion. The only step we have to do is we need to figure out our actual amount of medication to be given per minute by multiplying that by the patient's weight in kilograms. Make sure that our units of measurement match each other so that we can actually get the correct answer. The clock method. So this is another way that we can calculate our drops per minute for our infusion medications. The clock method will only work for an infusion. It won't work for fluid over time or a single dose med math problem. And the clock method works best when we have a medication that is concentrated 4 milligrams or 4 micrograms in 1 milliliter. So if we look at this problem here, I have a drug that I need to give 2 milligrams per minute with a 60 drop set, and I have it packaged 2 grams in 500 milliliters. This is an example of lidocaine infusion. Using my factor method, I can do 500 times 2 here. 2 times 2 is 4. Reduce that to 1 mass unit, and I have 4 milligrams per milliliter. Now that I have that step completed, I can move over to my clock and start filling that out so I can get my answer in drops per minute. So I'm going to use my concentration to start with my clock. The next piece is I need to take a look at my desired dose. Well, in this case, my desired dose is 2 milligrams per minute. So when I'm at my clock here, start right here in the middle, I'm going to simply go around my clock until I get to the dose that I want to give. So right here, I'm at 2 milligrams, which means I need to administer 30 drops per minute. So my answer to this would be 30 drops per minute, or I could divide that by 10 and I would give 3 drops every 6 seconds. So the clock method that I just showed you, while it works best with a medication like lidocaine that's concentrated 4 milligrams in 1 milliliter, the clock method will work with other infusion medication problems. So in this example, to show you this, I have 5 micrograms per minute as my desired dose with a 60 drop set, and my medication concentration is 4 milligrams in 250 mLs. This is an example of a norepinephrine infusion. So first step doesn't change. I need to reduce my medication concentration. So my factor method would be times 4, 4 times 4 here, and that's going to give me 16 micrograms per milliliter. Okay. Now that I have my concentration determined, I can move to my clock and start to set my clock up. So I'm going to put 16 at the top. 16 divided by 2 is going to put 8 here, which is going to put 4 here. 8 plus 4 is going to put 12 here. Next, like in the previous problem, I need my drip set here, which is 60. So 60 goes at the top, 15, 30, and 45. Now I'm ready to figure out what my drops per minute is. So my desired dose in this case is 5 micrograms per minute. So I'm going to come up here and I'm going to start moving around my clock until I get there. Okay, well, I'm at 4, and we can look at this and say, okay, if I'm at 4 and 8's here, then I know that my drops per minute that I'm going to administer is somewhere between 15 drops per minute and 30 drops per minute. So we're going to keep going, and we know that 5 comes right after 4. So that's going to be roughly 20 drops as my answer. So I would probably go ahead and start out and give 20 drops per minute. As most of our infusions have a range and we titrate that to a patient response. So 20 drops per minute is going to be something that I can do relatively quickly and easily with practice. You can do it in your head so you can get your medication infusion started and then make sure and confirm that you have an accurate dosing. So if we were to go through and do the formulas like we had previously done, we would get an answer of 18.75 drops per minute. And giving the patient 20 drops per minute is acceptable for this infusion. Throughout our lesson today, We have only been focusing on gravity fed medication fluid over time and infusions, and that just means that we're using a drop set, right? So a drop set here, either a micro or a macro uh, drip chamber to be able to calculate the drops per minute. Right? So when we're doing medication infusions using a drop set, because it's gravity fed, we need to calculate the drops per minute, and that's how we give accurate medication dosing. If we're trying to use an IV pump, now that's a different animal, because the computer inside the IV pump is going to calculate the infusion differently, right? The pump is not going to calculate drops per minute. The pump is going to need to use milliliters per hour, and it's going to give the correct amount of medication by calculating how much volume to give. And by calculating how much volume to give, it's going to give whatever desired dose that we input into the pump. Now, large variety of pumps, definitely be familiar with the ones that you may use or the ones you may be exposed to during interfacility transports. And it's also important for us to know how to calculate milliliters per hour. So when using a pump, we can input that data correctly. And at the same time, if the pump fails, we can then do the manual gravity fed drip calculations to get our drops per minute. To show an example of this, we can go back to the first clock method example that we did with lidocaine, where we wanted to give our patient 2 milligrams a minute of our infusion, and we had a medication concentration that we determined to be 4 milligrams per milliliter. And when we did our clock method calculations, we came out with an answer of 30 drops per minute, because we were using a 60 drop set. So our gravity formula and math had to account for the drop set that I was using. And for pumps, I need to determine the volume per hour that I need to administer. Well, the best way to do that is going to be to convert my ordered dose into milliliters per minute. And the way to convert that is to take 2 milligrams per minute and divide that by 4 milligrams per minute, or divide that by your medication concentration. So I'm taking my desired dose and dividing that by my medication concentration. That is going to give me 0.5 milliliters per minute, right? Because when I do this here, I'm going to cancel out the milligrams. All I'm left with is milliliters per minute. From there, my last step is I need to take 0.5 milliliters per minute and multiply that by 60. That will give me an answer of 30 milliliters per hour. And 30 milliliters per hour is what I would input into my pump, so the pump knows to administer 30 milliliters every hour. And by doing that with the medication concentrated correctly, we're going to be giving our desired dose of 2 milligrams a minute. In this case study, we're called out to an urgent care to transport a patient that's 6 months old, weighing about 18 pounds, with suspected measles to the hospital. The parents, when we get there, report that the child has not been eating very well the past few days and has had few wet diapers. Our assessment reveals the child is verbally responsive and their skin is hot to the touch, and we can see this classic rash consistent with measles on the patient's skin. We get a temperature of 103 degrees Fahrenheit, and our vital signs reveal a heart rate of 135 and a blood pressure of 66 over 40. So I want you to take a minute and write down some of the medications that this patient may be administered during the course of this call. So the medications that we may administer during the course of this call would be acetaminophen to treat the patient's fever, IV fluids for dehydration, and worst case scenario, the patient continues to become hypotensive despite fluid resuscitation, we may need to consider a vasopressor. So we're going to work all three of these problems in this case study for this child with measles. Is the first medication that I would want to administer. The dose for that in this case study is going to be 15 milligrams per kilogram, and that's going to be PO, which means we need to give this medication orally. Our patient's verbally responsive, but they're maintaining their airway and they're able to control their airway. So for this case study, we're going to be able to administer this medication the PO route. Next, we need to know how our acetaminophen is packaged. So we're going to pull that medication out of our bag and look at the bottle. And it's going to tell us that there is 160 milligrams in 5 milliliters. Perfect. So we have our desired dose, we have our concentration. We know that this is going to be a single dose formula, so we can go ahead and work this problem. First thing I would want to do is reduce my medication concentration down. Since 5 is going to go into 10, that's going to can use my factor method. So 5 times 2 is going to give me 10 milliliters. 160 times 2 is going to give me 320 milligrams. Okay, move my decimal place 1 place. So that tells me now that I have 32 milligrams per milliliter. Now we need to know how much our patient weighs. And I'm gonna write that down here in the bottom so we can keep track of it. So our patient weighs 18 pounds, and we need to convert that to kilograms. So if we do 18 divided by 2, that's going to give us 9. And then we need to subtract 10%, which means we're going to subtract 0.9, giving us 8.1 kilograms. So we're going to use 8 kilograms in our problem here. I'm going to do 15 times 8, and that's going to give me 120 milligrams total. So my last step is I just need to determine how many milliliters I need to draw up and give to my patient. So now I can input this information into my single dose formula. 120 milligrams is my desired dose. That's going to be divided by what I have on hand in this case, which is 32 milligrams. And then I'm multiplying that by the volume, which is 1, to see what my answer is. 120 divided by 32 is going to give me 3.75. That times 1 is going to give me an answer of 3.75 milliliters. And that's what I would draw up and administer to this patient to give my 15 milligrams per kilogram fluid bolus. While we're working on our acetaminophen, our partner has started an IV and is preparing to give a fluid challenge. For this fluid challenge, we want to give this patient 20 milliliters per kilogram over 10 minutes using a 10 drop set. Okay, so first step, we need to determine how much total volume we're going to administer. We know that our patient weighs 8 kilograms, so we're going to start with 20 times 8. And that's going to give us a total amount of volume to administer this child of 160 milliliters. Since we are dealing with a 6-month-old, if you have a volume chamber on your unit, this is the time to bring that out so we can control the amount of volume that we give to our pediatric patients. We don't fluid overload them. 160 milliliters is our total volume, and I am now ready to input this information into my fluid over time formula because it's over 10 minutes. So I'm going to take my total volume, which is 160 milliliters, multiply that by my drop set, which is a 10 drop set. And then I'm going to divide this by the total amount of time that I need to give this medication, which is going to be 10 minutes. I can cancel my milliliters out, so my answer is left in drops per minute. 160 times 10 is going to give me 1,600. 1,600 divided by 10 is going to give me 160 drops per minute. And then I can divide that by 10, and I'm going to give this patient 16 drops every 6 seconds. So with 16 drops every 6 seconds in 10 minutes, I've given this child a fluid challenge of 160 milliliters, and I can reassess blood pressure to see if there's been any improvement. Say that we give the fluid and we start to notice that the child is not responding well to the fluid challenge, and we determine that it's necessary to give a vasopressor to maintain permissive hypotension in our 6-month-old patient, and we decide we're going to utilize epinephrine for this vasopressor infusion. And the dose we're going to go in this case study is 0.3 micrograms per kilogram per minute. All right, I'm going to use a 60 drop set. 60 drop set. My medication is packaged by placing 1 milligram of epinephrine 1-to-1, which is your IM epinephrine, into a 500 milliliter bag of IV fluid. Now to start here, I'm going to go ahead and determine what my medication concentration is and convert milligrams to micrograms. With my factor method, that's going to be a factor of 2, which means I'm going to have a concentration here of 2 micrograms per milliliter. The next step is I need to determine what my desired dose is. So I'm going to take my desired dose here of 0.3 micrograms, and I'm going to multiply that by the patient's weight in kilograms, which is 8. That is going to give me a desired dose of 2.4 micrograms per minute. Awesome. I'm going to start with my desired dose, which is 2.4 micrograms per minute. I'm going to multiply that by my drop set, which is a 60 drop set. And then that gets divided by my drug concentration, which is 2 micrograms per milliliter. I can go ahead and cancel things out. So that tells me that I have my formula set up correctly because I'm left with drops per minute. I'm going to do 60 times 2.4, and that's going to give me 144. And then when I divide 144 by 2, that is going to give me 72 drops per minute that I need to administer to my 6-month-old as a vasopressor infusion. And then I probably would take that and divide it by 10 and just go ahead and give 7 drops every 6 seconds. And this is how we would do our medication math problems, in the field. Once you get good at this and you've memorized the formulas, then it's just as simple as plugging in a couple data points into a calculator and you're getting an answer that you can be confident is correct. The next case study I have for us is a burn patient. We have a 45-year-old patient that is burned on 30% of their body that occurred secondary to a gas explosion while they were camping. The patient weighs 160 pounds, and we need to utilize our Parkland burn formula to calculate this patient's fluid resuscitation needs. Now, our Parkland burn formula is a specific formula that we use just for burn patients, and it's 4 milliliters times the burn surface area, in this case is 30%, and that's multiplied by the patient's weight in kilograms. Now, that number is going to be given in the first 24 hours. for us in the pre-hospital environment, we need to do this math, and then we need to determine the amount of fluid we need to administer in the first hour to start our drip set. With this case study, the first thing to do is we need to input the data into our Parkland burn formula. So we know that we're going to need to give 4 milliliters times our burn surface area, which is 30%. And we're going to keep it as 30%. We're not going to reduce that down to multiply. We're just going to multiply 4 times 30. That is then going to be multiplied by the patient's weight in kilograms. Well, I said previously that our patient weighs 160 pounds. So we need to divide 160 pounds divided by 2 is going to give me 80. 10% of 80 is 8. So if I do 80 minus 8, that's going to give me 72 kilograms. So that's what I come over here and I plug into my formula, 82 kilograms. Right? When I do this math here, that's going to give me, when I multiply across 4 times 30 times 72, that's going to give me 8,640 milliliters to give over 24 hours. Over 24 hours. Now, I'm not going to have this patient for 24 hours. So I need to start converting that down to figure out how much I need to give per hour. Well, with the Parkland burn formula, half of the total amount of fluid that's given in 24 hours needs to be given over 8 hours. So I'm going to take 8,640 and I'm going to go ahead and divide that by 2. When I do that, that's going to give me 4,320 milliliters over 8 hours. And I know now that this is the amount of fluid that needs to be given over 8 hours. I need to now divide 4,320 divided by 8 to determine the amount of fluid that needs to be given in the first hour. That's going to give me 540 milliliters over 1 hour. And from here, this just becomes a fluid over time problem where I need to know what my drip set is. In this example, we're going to use a 20 drop set. Okay. I'm going to take 540, put this into my fluid over time problem, 540 multiplied by my 20 drop set. Divide that by the total time. And remember, I want to do it in minutes in this case. So I'm going to divide this by 60 minutes. And we are going to get 540 times 20 is going to give me 10,800 divided by 60, which is going to give me 180 drops per minute. And I would again divide that by 10, and I would give this patient 18 drops every 6 seconds. So this burn patient in the first hour is going to receive 180 drops per minute, and that's going to give me a rate of 540 milliliters over 1 hour.
There may be more medications and medication math that we need to do for our burn patient. For example, say they're hemodynamically compromised or have airway involvement, we may need to perform a drug-assisted intubation utilizing a sedative and a paralytic. The sedative for this example, we'll say that we use etomidate. Our dose for etomidate in this case is 0.3 milligrams per kilogram. And we already know that our patient weighs 72 kilograms. And when we pull our medicine out of our bag and we look at the vial, it's concentrated with 40 milligrams in 20 milliliters. Okay. So now we can start to work our problem. Well, the first thing we need to do is we need to take 72
and multiply that by 0.3. That will equal 21.6. So I need to administer, I'm going to round that up and say that I need to administer 22 milligrams of this medication. The next thing I would do is I would look at my vial and determine how many milligrams there are in a single milliliter. Well, most likely on the vial, it's going to tell us that there's 2 milligrams per milliliter. And if we can't find it, we can pretty easily do 40 divided by 2, and we know that that's 2. So for every milliliter, there's 2 milligrams of a drug. So then I look at my desired dose in this case, which is 22 milligrams, and I look at how my medicine is concentrated, and it becomes pretty easy. I know that I'm going to give at least 10 milliliters because 10 times 2 is 20. And if there's 2 milligrams in 1 milliliter, that makes my answer 11 milliliters that I need to administer. So this is just an example of trying to keep it simple in the field and remembering your single dose formula so that if the call is a bit too stressful and maybe this simple math just isn't something that your mind can process in the moment, you can plug this information into your calculator, on your watch, your phone, and get an answer, or just simply slow yourself down and look at it from as simple of a perspective as you can. Now that we have our sedative dose and we've pulled that medication up, we can move on to our paralytic. In this case, we'll use rocuronium and say that our dose here for rocuronium is going to be 1.5 milligrams per kilogram. And again, we know we have a 72 kilogram patient, and our medication in this case is packaged 100 milligrams in 10 milliliters. And we need to know how many milliliters we need to give to our patient. Well, same thing. We're going to take our desired dose and multiply it by the patient's weight. So we'll do that again right here. So it's going to be 72 times 1.5, which is going to equal 108 milligrams. Now I'm going to look at my drug concentration and see what I have. And I can see that 100 milligrams in 10 mLs, that's going to be 10 milligrams per milliliter. Perfect. That's going to make this really simple to figure out because I know that I'm going to give 10 milliliters and then I have 8 milligrams. That's going to be just under 11 milliliters. And to keep it simple, I'm just going to round it up to 11 milliliters. And my dose for my sedative and my paralytic is 11 milliliters. Also, be sure to label these medications so that you know which one is which so you can give them in the correct order when you're pulling these medications up. We may also need to administer a medication for toxic inhalation as our patient is showing signs of cyanide toxicity. That medication would be hydroxycobalamin. And hydroxycobalamin comes in a rather large vial that is 5 grams of our medication, and it's in a 250 milliliter vial. Now we're not going to pull all of that fluid out of this vial and place it into an IV bag because inside the box it comes with a transfer spike that connects it to a traditional drop set. So we can use any drop set that we want. So for this example, we grab a 15 drop set here, drops per milliliter, and we need to give this medication over 15 minutes. So this is going to become a fluid over time formula where I'm going to take my total amount of fluid, which is 250 milliliters, multiply that by my drop set, which is a 15 drop set, and then divide that by the amount of time that I'm giving this medication, which is 15 minutes. 250 times 15 is 3,750 divided by 15. is 250, and my answer is 250 drops per minute. 250 drops per minute is a pretty fast drip. It's going to be hard to count. So I would probably go ahead and divide 250 by 20 and try to count about 12 drops every 3 seconds. This is going to allow me to get as close as I can to 250 drops a minute, but with a 15 drop set, most likely this is going to be a wide open infusion for 15 minutes. Our last case study is a cardiac call, and we get dispatched out to a 78-year-old male experiencing lightheadedness and nausea. On arrival, our patient's telling us that they're feeling a fluttering sensation in their chest that began shortly after finishing dinner. The patient is conscious, alert, and oriented times 4, and our 12 lead reveals what we would call ventricular tachycardia. Now, because this patient is conscious, alert, and oriented times 4, they're considered to be stable, and we would not go straight to cardioversion in this case. We can try some sort of pharmacological intervention first. Local protocols can vary as to which medication you may use. In this case, I'm going to use amiodarone. And the first dose of amiodarone here that we want to give is 150 milligrams in 100 milliliters over 10 minutes using a 10 drop set. So because it's over a set amount of time, this is another fluid over time formula. I just need to make sure that I remember to put the 150 milligrams of my amiodarone into the 100 milliliter bag of fluid. If I don't do that, then I'm not giving the medication. Once I get done with that, I can set my problem up, and I'm going to give 100 milliliters times a 10 drop set divided by my time in minutes, which is 10 minutes. Milliliters will cancel out. 100 times 10 is 1,000. Divided by 10 is 100 drops per minute. And that's going to equal out to 10 drops every 6 seconds. So for this case study, we give our initial bolus of amiodarone, and it converts our patient's ventricular tachycardia back into a sinus rhythm. So because our amiodarone worked, we're going to want to hang an amiodarone maintenance infusion to prevent the tachycardia from reoccurring. For our maintenance infusion, we're going to take 450 milligrams of amiodarone, and we're going to place that into 250 milliliters of fluid. And we need to give a desired dose of 1 milligram per minute using a 60 drop set. Okay, I'm going to use the clock method for this. So I'm going to go ahead and use my factor method. 250 times 4 is 1,000. 450 times 4 is 1,800 milligrams. And I have 1,000 milliliters. Now, the reason I kept it in milligrams is because my desired dose is in milligrams. So I'm going to keep it this way and then convert it down. Now that I have 1,000 here, I need to move my decimal place 3 places to the left on both sides. 1, 2, 3. It's going to give me 1.8 milligrams. 1, 2, 3. That's going to give me 1 milliliter. Okay. Now that I have this done, I can start to set up the clock method here. So we're going to start with 1.8 at the top. All right, 1.8 divided by 2 is 0.9. Well, 0.9 divided by 2 is 0.45. And then 0.9 plus 0.45 is 1.35. Then I just need to take my drop set and write this at the top: 60, 15, 30, and 45. And I want to give my patient 1 milligram a minute here. So we're going to start yellow, start up. So we're not there yet. So we're at 0.9 at 30 drops per minute. So we know that's going to be just right in here. So we're going to go ahead and call that 30 drops per minute is what I'm going to administer to this patient. So 30 drops per minute will give me my desired dose of 1 milligram per minute. And this is using the clock method to find this answer. As we're running our amiodarone maintenance infusion, I think it's also good practice to start thinking ahead. So in this case, we may want to prepare ourselves for what we would do if the ventricular tachycardia reoccurs. And in this case, they would become unstable. So we would definitely want to place the cardiac pads in our patient so we can immediately intervene. And we may also want to think about midazolam so that we can provide our patient with a medication to help make that procedure more comfortable, or at least allow the patient to forget about the pain of us shocking them. So midazolam, our dose for this case study, we're going to go with 2.5 milligrams IV. So that's our desired dose in this case. And when we pull our midazolam out of our bag, it's going to be packaged here in this case 10 milligrams in 2 milliliters. Well, we can look at that pretty easily and say that I have 5 milligrams per 1 milliliter. And just by keeping it simple and looking at it like this, I know that if I draw up 0.5 milliliters, that is going to give me the 2.5 milligrams that I would need to give to my patient. So I can go ahead and get that medication out, know exactly how many mLs I need to draw up, so that if we do need to give this medication, we already have our dose predetermined and ready to go.
Thank you for sticking with me today. We've covered a lot of material. Please remember that medication errors are common, even in pre-hospital medicine. And medication math competence affects both experienced providers and newer providers. And our underreporting of medication errors complicates our understanding of this problem. And we should work to create a culture within pre-hospital medicine where we can report medication errors and determine ways to mitigate and learn from those mistakes so that they don't happen again, as opposed to a consequence culture where reporting those errors is tied directly towards punitive punishment. Understanding units of measurement and how to convert between different units of measurement, as well as how to reduce a medication concentration down to the amount of medication in 1 milliliter, are critical steps in being able to determine accurate medication dosing calculations. Remember the formulas that we talked about today, such as the fluid over time, our single dose formula, and our infusion formulas, and put the clock method in your toolbox so that when you are in a scenario that's high acuity and high stress and using a calculator is not feasible, you can use the clock method quickly and accurately to begin your medication infusion for a patient. And lastly, medication math is a perishable skill, and we should train this regularly so that we are able to perform this skill reliably in the field. Thank you again for watching. We'll see you next time at CE Solutions.